Okay, so now we can move on and investigate in a little bit more detail how individual collisions affect gravitating systems, right? It's really just an analog of the process of Coulomb collisions in a plasma that we've looked at in a lot of detail before. Again, without the existence of positive and negative charges to have either attractive or repulsive interactions. They're all attractive in this case. And we would like to look at their sort of aggregate effects on a large system. And we already sort of know what those aggregate effects are going to be, right? And there were sort of two of them that were always balancing each other out in a plasma. We've studied all the way since the Langevin equation, right? There's the fact that collisions randomize the motions of particles and thus produce diffusion in velocity space. But then you also have the slowing down or frictional effect, right? If a fast particle comes in, it'll get slowed down by these collisions. So we'll think a little bit about both of those. You know, the setup of the individual hyperbolic deflection event is pretty much exactly the same as it was in a plasma. We will, in this video, we're going to stick again with just the small angle events, because we already know that if the Coulomb logarithm is large, the small angle events will be more important in the aggregate than the large angle small impact parameter events. Right, so we can use this approximation that the actual impact parameter is much bigger than V min, which we derive and which we essentially define in exactly the same way that we did before, except that in the magnitude of the 1 over r squared force, there's a GMM instead of a Q1 Q2, and that just gets plopped right into the definition instead of the Q1 Q2. Because of now these different units, it's interesting that some of the masses can cancel out, right? The reduced mass between the two bodies has an M1, M2 in it. So all that's left over is a total mass. And this is sort of something we saw, this replacement is something we saw in Kepler's third law as well. Yeah, so it sort of simplifies the definition of the minimum impact parameter. In the gravitational world, the standard minimum impact parameter that we defined, if you remember, that corresponded to a deflection angle of something like 53 degrees, almost 1 radian, just in the way that we defined it. If you look at a slightly smaller minimum impact parameter, basically that our classical B min divided by 2, that gives you a larger deflection angle of 90 degrees, and that tends to be the definition that gets used for the inner definition of the integral from B min to B max. They start at this B90, and actually that sort of just simplifies the definition as well. For two equal mass bodies, our B min would have been 4 GM over V squared, so it's just 2 GM over V squared. Yeah, but that's just a factor of 2 in the definitions. So if you use that and you turn the crank on that whole sort of target board integral over all the possible impact parameters from B min, which is now B90, out to, well, infinity or B max, or now if we set B max as the size of the system, I'll sort of just define this thing as the radius of the galaxy, or some sort of size scale that represents the overall size of the system that we're looking at. If you do that, we eventually get the same answers as before, just with different factors in them, right? Instead of the Q1, Q2, there's the GM. We get the slowing down time scale, we get the perpendicular diffusion time scale as I wrote here, and it's all really the same derivation. It's nice in the way the course is set up now that we've already sort of done all the heavy lifting in deriving that, so I can just give you that result. And again, remember, we set this this finite time interval delta t as this finite thing that represents the length of the cylinder. And if you make that longer, there's going to be more deflections. So it's nice that the gravitational deflection is proportional to delta t. For longer elapsed times, there's more and more velocity dispersion. So the way that this is often thought about in galaxies is Well, maybe we'd like to solve for that time scale. In other words, how long would you have to let this thing go before some particle that's flying in with an initial velocity eventually gets so deflected that its perpendicular, that its RMS perpendicular velocity, it started off as all parallel, but it eventually becomes randomized. But when that delta V perp squared starts to grow to be of the order of the initial velocity squared, that is sort of a representative time that we're going to call the relaxation time, because that essentially means that after that amount of time elapses, the star has sort of completely randomized, thermalized maybe, and essentially forgotten about that initial direction and its initial condition from where it came from. Okay, so if we do that, we set the delta V perp squared equal to the initial V squared, and we solve for the delta T. And for the rest of this video, when we plug in these velocities, we're going to think of them as sort of representative thermal speeds of the random motions, which is sort of like the initial condition of any two objects that are going to come towards each other. They're going to both be sort of sampling from that same distribution. So the thermal speed, or the representative sort of gravitational speed of a system, is something that we can consider known. And we can solve for this relaxation time. So it's really just a function of that velocity, the masses of the objects, the number density, how many are in a certain volume, and this Coulomb logarithm. So it's something we can compute, and we're going to do it. And we can compare the relaxation time with some other known properties of a system, right? There's the lifetime of the system, or the age, right? How long has it been around? And there's also this dynamical time, or crossing time, that you can just get by taking the size of the system and dividing it by that representative velocity. In other words, how long does it take for some random object to cross over a path length of equal to the size of the system? And if the relaxation time is small in comparison to either of those, then that means the collisions are doing a lot over these important macroscopic timescales. If the relaxation time is large compared to those two things, that means collisions are unimportant to how the system evolves. All right, so we're going to do that for three examples: the Milky Way, a typical globular cluster, and a typical open cluster. But let's work with this expression a little bit more, because sometimes we don't know precisely all of these things. And there's a sort of a simple model that we can create that allows us to boil this down to a much simpler way of thinking about it. So let us think about some galaxy that's sort of a spherical, self-gravitating system filled with n identical stars. Again, this spherical system is, you've heard all the jokes about the spherical cows. We're simplifying things a whole lot here, but this is astronomy. We often try to do these back of the envelope analyses. And in this case, it really does provide something useful. So let's think about a spherical system where all the stars are moving around randomly. And, more often than not, if you pick a random star, it's not going to be right at the center. It'll be sort of somewhere out towards the edges. And the representative velocity that it will be feeling is going to be something like, from the Vis-Viva equation, something like gm over r. Again, where the m is the mass of this entire thing, the self-gravitating mass of the galaxy. A test star will be feeling that mass if it's sort of off to one side. And the orbital distance is going to be something on the order of the size of the galaxy as well. And again, if we know it's a spherical system containing n stars of identical mass, we can write the mass of the galaxy just as the number times the mass of each star. We can write the number density as n over some r cubed, r galaxy cubed thing, just by the volume. And these things can be plugged back into the relaxation time. And of course, the relaxation time contains the Coulomb logarithm, Bmax over Bmin, which is now the size of the system divided by this B90. We can write out the B90, as we just said a couple slides ago, rearrange some of these things, use the Vis-Viva equation, and amazingly, the what we called the plasma parameter before, is essentially just the number of stars in the system. Yeah, there's a factor of 2, but it's roughly the same. When you take the logarithm, if it's a large number, the logarithm of lambda and the logarithm of n are pretty much the same thing. Log of 2 is small compared to the log of 10 to the 11 or something. Yes, so, okay, we've got that piece, and we can take all these other pieces and put them into the velocities and sizes and masses and number densities, and we can write the ratio of the relaxation time to the crossing time, dimensionless ratio, and it boils down to just a simple function of the number of stars, n. It's not proportional to n, it's proportional to n divided by the log of n, but if it's large, that'll still be a large number, and there's a stray factor of 6 in there also. Yeah, but still oftentimes for big systems, this ratio is still going to be much larger than 1. And there's a reference I'll put in the description where you can find more precise versions of these things. But yeah, let's actually plug it in and look at these 3 sort of sample environments. We've got our own galaxy, a globular cluster, a small little satellite galaxy that's off in the halo of larger spiral galaxies like ours, and these little open clusters that aren't galaxies at all. They're just star-forming regions within our own galaxy, but they form a large number of stars, and they sort of start out self-gravitating, so we might as well think of them in the same sort of category. Yeah, there's a large range of sizes, right, from tens of thousands of parsecs just down to 2 parsecs. There's a range of representative velocities, depending on the masses mostly. So the crossing times are sort of all in the same, the large divided by large, small divided by small. The crossing times are kind of similar. The lifetimes, well, we know the Milky Way galaxy and the globular cluster. Globular clusters have been around for most of the age of the universe so far. Open clusters are much younger, and they dissipate when the stars sort of reach the main sequence. Right, so well, let's just look at each of these in turn. For the Milky Way, we know there's something like 10 to the 11 stars in it, or 10 to the 11 solar masses worth of stars. So we can compute that ratio. That ratio is almost 1 billion. So that means that if the crossing time is almost 1 billion years, the relaxation time is going to be much, much older, much, much longer than the age of the universe. This is the fundamental calculation that tells us that for large spiral galaxies, large elliptical galaxies, also individual Coulomb-like collisions are unimportant and irrelevant. So again, the videos next week will all be applied to large systems like that, and we're not going to take collisions into account. Okay. So the next example are the globular clusters. You've seen pictures of them, jewel boxes of space, they sometimes call them. They have hundreds of thousands of stars in them. So the ratio at the top there is something like 1,000. They're small, so the crossing time is not that large. So when you work out the relaxation time, if the crossing time is about 1 million years, the relaxation time is now about 1 billion years, since it's a factor of 1,000. And that's shorter than the lifetimes. So that means that collisions are important. Collisions probably have influenced the evolution, at least of the central regions, of globular clusters. We see examples of that when we look at the stars in globular clusters. There seem to be some interesting things called blue stragglers that might be the products of actual true collisions between stars. And also, because the relaxation time is so short compared to the lifetime, that's probably why they look the way they do, right? They might have started off as something with some, consistent angular momentum, but with so many collisions happening over the lifetime, they've randomized and become globular like we see them. It's sort of this relaxed random distribution of speeds and positions. Okay, last example is the open cluster, small star-forming region within our galaxy, only about 100 stars in there. So this ratio at the top is only about 3. So this is starting to tell us that collisions are playing a very important role. The relaxation time is only about 15 million years, again, shorter than the lifetime. And indeed, for these things, we actually think collisions are probably responsible for ending their lives. In other words, the collisions, it's such a small number of things that just a few collisions that happen and eject stars out into other regions of the galaxy, that is what sort of sets the maximum lifetime. Yeah, it's responsible for dissolving the clusters eventually. Okay, I hope that was a useful sort of look at some specific numbers. Yeah, so all of that derivation, all of that look at the relaxation time just had to do with sort of the one piece of what collisions do to a system, right? That's the randomization or diffusion in velocity space. But of course, there's this other thing. There's the slowing down, the dynamical friction that can happen. And we should look at some of the results of that. This often involves larger things, not just individual stars interacting with each other, but larger things like, say, a satellite galaxy, like one of these globular clusters, or something larger like the Magellanic Clouds that are orbiting the Milky Way. As that satellite galaxy is plowing through, it's colliding with stars and gas and dust and all sorts of things. And the dynamical friction effect can essentially slow it down and create orbital decay, where that small satellite galaxy eventually spirals in and gets consumed by the larger galaxy. The other example that we often see, and in our own department, Julie Comerford studies, is the idea of multiple supermassive black holes in the cores of galaxy. How long do they last before they eventually orbit around and lose energy by dynamical friction and spiral in and merge with one another? Those are both effects of multiple gravitational collisions. We won't look at the second one that much right here. I would just like to say a few more words about this satellite in spiral idea. There's more in Binney and Tremaine's book about it. But it's interesting how, if you follow the physics of it, it actually boils down to a very similar type of timescale ratio that we just derived for the relaxation time. So we've got this mass, this object that's orbiting the galaxy of a mass m galaxy. You can do the same sort of estimates from the Vis-Viva equation, and you can write a crossing time just like we did before. And if you go through the whole slowing down equation, Binney and Tremaine went through the process and sort of solved a special differential equation for the overall time over which this thing spirals all the way into the center. That ends up looking like this. And if we were to take the relaxation time and plug in some of these things, we would have gotten something similar, because eventually, if you take this version of the frictional in spiral timescale and divide it by the crossing time, guess what? You also get an n over log n with a slightly different numerical factor out front, where again, here the n is the mass of the galaxy over the mass of this inspiraling object, slightly different application. But yeah, it's a very similar scaling in terms of a dimensionless number. And the one thing that we can look at are our neighboring, large and small Magellanic Clouds. And if you plug in the numbers for them, you'll get something like 10 billion years, which, it'll eventually happen. It's a long way off. But interestingly enough, we know from the overall dynamics of our local group of galaxies that something even sooner, even more dramatic is going to happen. And that's only in about 4 billion years. The Milky Way and the Andromeda spiral galaxy will collide. I just provide the little film strip that's often shown in astronomy classes for what that, sort of an artist's conception of what that will eventually look like over the next few billion years. And we'll all sort of merge into a single elliptical galaxy at the end. But yeah, okay. I think that was it for the cumulative effects of small Coulomb collisions. The next video will specifically look at the rarer but possibly more dramatic direct actual impacts, very small impact parameter events that would normally provide a large scattering angle, but if the physical sizes are big enough, it'll actually cause a true impact-like collision.